Hi, my name is Bailey Chambliss, and this is my Physics 2212 Lab Number 6, Magnetic Braking with Faraday. So the purpose of this lab was to observe the relationship between a time-varying magnetic field to a curly external field as related by Faraday's law, as well as to create a computational model that can clearly and accurately predict this relationship. So my analysis came from collecting time data from a falling magnet through a conductive tube of aluminum foil, then model the interaction between the magnet and the tube computationally, and then compare the computational predictions to the observed data. Our results were that the real-world model measured an average total time in the tube of 1.534 seconds, the computational model measured a total time in the tube of 1.118 seconds, and the computational model demonstrates when the forces acting on the magnet are balanced and unbalanced. So our fundamental principles in this lab are Faraday's law, which is that EMF is equal to d phi over dt, the Biot-Savart law, which is that the B field is equal to mu naught over 4 pi times the charge times the cross product of velocity in r hat over r squared, and then Newton's second law, which is force equals mass times acceleration, Newton's third law, which is that the magnitude of the force on the falling magnet is equal to the magnitude of the force on the tube. And then finally Lenz's law, which is that epsilon is equal to negative n over d phi dt. So our experimental data, which came from doing this in lab, on the left-hand side we have our trials, our time it took for the magnet to fall through the tube, and then the average of all those times. Our initial conditions were that the length of the tube was 0.46 meters, the inner radius was 0.03 meters, the outer radius was 0.04 meters. Our mu, which we calculated in lab number 3, which was 3.8837 am squared. Our magnet mass was 0.0025 kilograms, and our average time was 1.534 seconds. So our checkpoint questions: why can't we use a ferrous tube, for example, a steel pipe? This is because the magnet would be attracted to the tube, therefore it would either fall much slower or not at all. This would skew the results or even lead to no results. What happened to the magnet? How does this compare to a magnet falling in free space without a tube? So when a magnet falls in free space, there are no extreme resisting forces preventing it from falling besides the force of gravity. However, this changes when the magnet falls to the tube. The tube is conductive, therefore it experiences the resistive forces that oppose gravity, making the magnet fall more slowly. So this is the GlowScript code that I use. It's also linked in the PDF file, but all of these screenshots are the parts that I edited. A lot of it came from our initial conditions as well as code from previous exams, and then filling in other places as needed. So this is the GlowScript result. So our results and conclusions. According to the protocol, the intensity of the coloring on the tube is an indication of the magnitude of the current flowing through each of the rings. Red versus blue, the current flows in opposite directions. So our potential sources of error can come from discrepancies based on the value of mu from lab 3, errors in timing of the magnet through the tube, and just other human error. Which color corresponds to clockwise and counterclockwise current? Red indicates the clockwise current and blue indicates counterclockwise current due to its resistance against the increasing of the magnetic flux. What happens to the dynamics of the system when you flip the magnet around? This would not change the velocity or speed, but the directions of the currents would be flipped. How does the total in time and tube of your real-world system compare to the computational model? The time and tube of the real-world system is longer than that of the computational model. This can be contributed to by human error or other things we might just not be aware of. What does the shape of the velocity versus time plot tell you about the forces acting on the magnet? The shape suggests imbalances in forces, then constant velocity, and then imbalance as the magnet increases in its velocity. So our discussion questions: what if the resistivity of the conductor were reduced as close as possible to 0? How would the dynamics of the falling magnet change? The induced current would have to be much larger, therefore the magnet would take much longer to fall through the tube. What if holes or slots were cut into the tube? How would this affect the ring currents in your model? If holes or slots were cut into the tube, the magnet would drop faster because the magnetic force and induced current would decrease due to the loss of surface area of the tube. Thank you.